Hello everyone, welcome to my class. In today's class we are covering cylinders and quadric surfaces. Let me start the class right away. So far we have studied two special types of surfaces, planes and spheres. Note that the planes are the surface in 3D described by the first degree equations ax plus by plus cz plus d equals to 0. Here we investigate two other types of surfaces, cylinders and quadric surfaces. First, let me start the cylinders. Quick definitions. A cylinder is a surface that consists of lines called rulings parallel to a given line and passing through a given plane curve. Its equation consists of any two of the three variables x, y, and z. While sketching, the missing variable can take any value and its shape does not change. Note that a cylindrical surface does not need to be circular. Quick example. In R3, the graph of x square plus y square equals to 4 is a circular cylinder with rulings parallel to the z-axis. And the graph of z equals to 1 minus x square is a parabolic cylinder with rulings parallel to the y-axis. Let me visualize. The idea is draw at least three traces which provide a framework for the surface. The first diagram here, this is x square plus y square equals to 4. Here the z variable is missing. So first, graph x square plus y square equals to 4. It's a circle in xy plane. And since z variable missing, we can move this circle up positive z directions as well as down to the negative z directions. So that means we are basically piling up circles over circle and we got this circular cylinder. I hope this makes sense to you all. And here the shape does not change. This is another important feature. Similarly, in the next diagram on my right side, so next the diagram towards my right side, let's graph z equals to 1 minus x square. So here when x is 0, z equals to 1, so that means it crosses the z-axis at 1. So this is a downwards opening parabola. Let's draw at least three traces. So one here, and one here, and one here. And then this gives a cylinder, but this time this is a parabolic cylinder. So its shape looks like kind of, if you are visualizing, the shape is this shape here. I hope this makes sense to you all here. Great. So now let's move on. Next, let's talk about quadric surfaces. The graph of a second degree equations in three variables x, y, z, such as x square plus by square plus cz square plus dxy plus exz plus fyz plus gx plus hy plus iz plus k equals to 0 with at least one of the coefficients of second degree. Here's a, b, c, d, e, or f being non-zero is called a quadric surface. Quick note, the quadric surface are the counterparts in R3 of the conic section in R2. There are 6 standard surfaces we study: ellipsoid, an elliptic paraboloid and hyperbolic paraboloid, elliptic cone, and hyperboloid of one seat and hyperboloid of two seats. Quick alert, sketching surface is way trickier and more complicated than the plane. Its shape changes along the directrix. Note, to find the traces in the coordinate planes, that is in xy plane put z equals to 0, in xz plane put y equals to 0, and in yz plane put x equals to 0 respectively. So 6 standard surfaces, each can be described by a second degree equations of the form below. First, let's talk about ellipsoid, whose standard equation is x square over a square plus y square over b square plus g square over c square equals to 1. Its counterpart in R2 is ellipse. Now here is an ellipsoid in 3D. So quick note, its traces in the coordinate planes are all ellipses. First, draw 3 traces at each intercepts. At x equals to plus minus a, y equals to plus minus b, z equals to plus minus a. The ellipsoid is symmetric with respect to each coordinate planes. And in particular, if a equals to b equals to c, then this is the equation of sphere. Awesome. Now let's do quick visualizations here. Sphere, it's a football shape. Right? Quick example. Sketch and identify the surface given by 9x square plus 4y square plus z square equals to 36. Let's rewrite in this standard form. Divide by 36, it gives you x square over 4 plus y square over 9 plus z square over 36 equals to 1. So here, let's find the intersections point. This sphere crosses the x-axis at x equals plus minus 2, y-axis at y equals to plus minus 3, and at z-axis at z equals to plus minus 6. Then mark those points on this 3 dimensions here. Then on xy plane, it's an ellipse, x square over 4 plus y square over 9 equals to 1. That is this pink ellipse. Similarly, in YZ plane, put x equals to 0. So it's another ellipse with y-intercept plus minus 3 and z-intercepts plus minus 6. So z-intercept plus minus 6 and y-intercept plus minus y plus minus 3. So it's this outer ellipse. And in xz plane, y equals to 0. X-intercept plus minus 2, z-intercept plus minus 6 is this brown ellipse. I hope this makes sense to you all. So this all 3 traces gives us a framework of this ellipsoid. Awesome. So let's move on. Next, hyperboloid of one sheet. Just the equation of ellipsoid, all positive here. Now here is a 1 negative. Either it can be here minus x square, then x-axis will be the directrix. Here's z is minus, so that means z-axis is the directrix. So quick note, its traces in the xz and yz planes are hyperbolas, whereas in the xy plane it's an ellipse. So that means if you put z equals to 0, then we will have x square over a square plus y square over b square equals to 1. So that's our ellipse. And if you put y0 or x0, then in the xz and yz plane it's a hyperbolas. The variables with the negative sign corresponds to the directrix. So the z-axis is our directrix. Draw 3 traces at z equals to 0 and at z equals to plus minus radical is denominator. So that means let's draw 3 traces at z equals to 0, that means on xy plane, and at z equals to plus minus radical c height. I hope this makes sense to you all. Let's do quick example 2. Sketch and identify the surface given by 4x square plus 9y square minus z square equals to 36. Let's divide by 36. X square over 9 plus y square over 4 minus z square over 36 equals to 1. So the z has a negative sign, so z-axis is the directrix. Here, I forget to draw the z-axis here. So what's the idea to sketch? this is the solution here. So directrix is z-axis because it's the negative sign here, and we are sketching at z equals to 0 and z equals to plus minus radical 36 6. So at z equals to 0 we have ellipse x square over 9 plus y square over 4 equals to 1, x-intercept plus minus 3, y-intercept plus minus 2 is this small pink ellipse here. X equals to 3 3, y equals to 2 2, and at z equals to plus 6 and minus 6 height, so from here 1 2 3 4 5 6, similarly from here 1 2 3 4 5 6, at z equals to plus 6 height and at z equals to minus 6 height, we have this ellipse is a bigger ellipse, bigger ellipse than the previous one. So here x-intercept is this is radical 18 means 4 point something, and radical 8 means almost 3. So then we construct a ellipse here, and then in other plane, xz plane and yz plane, it's a hyperbola, so it's joined by this way. Then this gives us a nice shape hyperboloid of one sheet. Great. I hope this makes sense to you all. Now let's move on. I hope this makes sense to you all. Now let's move on. Now 3 hyperboloid of 2 sheets. Its equations is of the form the same as the hyperboloid of one sheet, but it has 2 minus here. Either this minus in the of z or x, or the minus is on for x and y, or the minus is on for y and z. So here I put for x and y so that z axis will be the directrix, so it's easier for us to visualize. Great. So note its traces in the xz and yz planes are hyperbolas, whereas in the xy plane it's either ellipse or no trace. The 2 minus sign indicates 2 sheets, and the variable with positive sign corresponds to the directrix. So the example 3, sketch and identify the surface. We write these equations in this form, then we can compare. So it has 2 minus sign, that means, and to the right side is 1, so that means it's a hyperboloid of 2 sheets. We're not interested on this one, so I didn't sketch the graph. So let's move on. Cone. So in these equations, on my right side is 0, and I have 1 minus sign either in front of z or in front of y or in front of x. So here I put on minus z so that I can visualize the cone just standing there or upside down here. Great. So quick note, its traces in the xz and yz planes are either hyperbolas or 2 intersecting lines at the origin, whereas the traces in the xy plane is an ellipse. The variable with the negative sign corresponds to the directrix. So here the z-axis corresponds to the directrix. And draw 3 traces at z equals to 0 and at z equals to plus minus radical, its denominator. Quick example 4, sketch and identify the surface given by 4x square plus 9y square minus z square equals to 0. Let's rewrite. Let's take the LCD of 4 and 9, which is 36. So divide both sides by 36. We have x square over 9 plus y square over 4 minus z square over 36 equals to 0. So keep in mind, in the equation of cone, we have 0 on our right side. So the z variable has negative, so directrix is z-axis, and draw the sketch at z equals to 0 and at z equals to plus minus 6. At z equals to 0, we have x square over 9 plus y square over 4 equals to 0. Sum of 2 positive numbers 0 means both x and y has to be 0. So then we got the just point in origin here. I'm talking the graph now. And at z equals to plus minus 6, so at here 1 2 3 4 5 6. Similarly 1 2 3 4 5 6. At z equals to plus 6 and minus 6, we have so z square means 6 square, 36 cancel, that is a 1. Take 1 to the right side, we have x square over 9 plus y square over 4 equals to 1. It's a ellipse, x-intercept plus minus 3, y-intercept plus minus 2. So then this is x-intercept 3, y-intercept 2, this ellipse, and here this ellipse. And we know the cone has two lines crosses at origin, so you just draw these two lines. Now it's a cone. I hope this idea makes sense to you all. Now let's move on. The fifth one is paraboloid, whose equation is of the form x square over a square plus y square over b square equals to z over c. So one variable has our first degree here. I hope this makes sense to you all. Either z or x or y. Then this represents the paraboloid. Quick note, its traces in the xz and yz planes are parabolas. Yeah, if you put here y equals to 0 or x equals to 0, then it gives the parabola. Whereas in the xy plane, put z equals to 0, it passes through the origin, or z equals to any other number, let's say c, then this is x square over a square plus y square over b square equals to 1. It's an ellipse. The linear variable, the z variable here, corresponds to the directrix, and plus sign in front of it implies paraboloid opens upward. If z is positive, opens upward, z is negative, opens downward, and draw our traces at z equals to LCD of all coefficients of x, y, and z. That's the idea. Let's do a quick example. Sketch and identify the surface z equals to 4x square plus y square. Divide both sides by the LCD of 1 and 4, which is 4. So z over 4 equals to x square over 1 plus y square over 4. So then quick idea here. So directrix is z-axis, opens upward. Z has positive sign, so open upward. And at z equals to 4, at 4 height, here's 1, 2, 3, 4 height. We have ellipse x square over 1 plus y square over 4 equals to 1. So x-intercept 1, y-intercept 2. X-intercept 1, y-intercept 2. Oh, it has 4 here, so let's say 1 and 2. It's a paraboloid. I hope this makes sense to you all. Now, the last one is hyperbolic paraboloid, which has 1 minus sign here, and just these equations here. Awesome. So whose equation is of the form x square over a square minus y square over b square equals to z over c. Note, its traces in the xz and yz planes are parabolas. So these are the parabolas. And in the xy plane, it's an hyperbola. The linear variable corresponds to the directrix. So it's hard to sketch obviously the quadric surfaces. So it's a saddle shape. I mean saddle of the horse. So that means there is no max or min. If we walk one direction, we have a maximum. If we walk another direction, we have a minimum. So then that's also called a saddle point in our later when you cover a maximum and minimum of the surface. So it's just a quick visualizations here, and there is a note that corresponds to the again maximum and minimum in sections 14.7. I'll cover there. So I hope this finish these sections. And one more final comment. Yes, the sketching surfaces is far more complicated than sketching the profile of the curve or the planes. So this is just the visualizations for you. So at least please try to recognize the shape of the surfaces by looking the equations of these second degree equations here. I hope it makes sense to you all. Thank you.